Now that we have seen how to find the sum to infinity, you notice it's not really necessary for us all the time to try and find limits as n approaches infinity. We can actually do that with our general expression of Sn and just derive, like what we've done with everything else, from basic principles. We actually end up with something that really defines our sum to infinity, right? If you remember what we said that once you have actually seen that your sequence converges, that is r less than 1 but greater than minus 1, right? Then if we go back to what we said, that the sum of n terms of a geometric progression is a 1 minus r to the power n over 1 minus r, right? And we are now in agreement that, okay, fine, for this particular sequence, our common ratio is actually a simple fraction, therefore the sequence should actually converge. The series, if we're going to add the terms, should also converge, right? Now, if that is the case, doing exactly what we've actually just been doing now, you will notice, if we want now to find the sum to infinity, that is infinity. As we've done before, this will be the limit, as n approaches infinity, of the sum of terms. That's a 1 minus r to the power n over 1 minus r. But remembering what we said, r is a simple fraction. We are talking of a fraction such as we've said before, 1 over 5. Or in general, x over y, provided x is less than y in terms of the absolute value, right? And if you notice, if we say n approaches if we say n approaches infinity, as n becomes bigger and bigger and bigger, and this is our ratio, then we are saying the ratio, this which is exactly the same as that, our y is going to grow much, much bigger than x, or our y to the power n will be growing much, much faster than x to the power n, and eventually we will approach 0. We have seen that. I just gave you an example of that if we were to try to share an orange, the whole of South Africa, 50 million people trying to share one orange, we will essentially get 0 each. Basically nothing. Right? Now if that happens, remember this is exactly the same as r to the power n. Therefore, all we are saying is, if you look at this, the only term which is being affected by n is this one. And we are saying this approaches 0. Right? So, if we were to rewrite this, therefore, our sum to infinity will be equal to a 1 minus, that approaches 0, 0 over 1 minus r. 1 minus 0 is obviously 1. So we are left with a over 1 minus r. So in general then, we can go on to say the sum to infinity of a converging geometric series is s infinity, which is equal to a over 1 minus r. And that's in general. We have derived this together. We are not copying it from any formula book, which is good. Now, let's take a look at an example. Or in fact, we are going to take a look at 2 examples to see how we can actually use that. Suppose we have got the following converging geometric series, which I'll give you now. Halves plus a quarter plus 1 over 8 plus 1 over 16 plus. You will agree with me, guys, that we are looking at a geometric series here. How do we know that? Obviously, as we have said before, our first term, like with any other series or sequence that we come across, we always have a first term. Our first term here, a, is equal to half. Correct? Good. Now, you also notice, if you want to find our common ratio, how do we do that? We've said that we find our common ratio simply by taking a term, dividing it by its predecessor, and then we see if that ratio is actually a constant. So we'll probably let's pick up all the terms that we have there. So obviously this will be term 1, this will be term 2, this will be term 3, this will be term 4. Okay? Tn over Tn minus 1 should give us our common ratio if for sure we are sitting with a geometric progression. Agreed? Good. If that is the case, then let's pick up T2 over T1. Obviously that will be equal to a quarter divided by half, which is the same as multiplied by 2 over 1. And you see that this actually gives us half. Good. If we pick T3 and T2, a term and a term before it, T3 over T2, that will be 1 over 8 divided by a quarter, which is the same as multiplied by 4 over 1. Again, we get half. If we do the same, T4 over T3, that will be 1 over 16 divided by 1 over 8, which is 1 over 16 multiplied by 8 over 1. We again get half. So we should convince ourselves, therefore, that we're sitting with a geometric progression here. We're sitting with a geometric series. Right? More important, while we have seen that, we're sitting with a geometric series. The other thing that we notice is that our common ratio is half. It's a simple fraction. It's a number between -1 and 1. Therefore, we will agree immediately that this series should actually converge. Sorry about that. Because R is actually a number sitting between -1 and 1. It's a simple fraction. If that is the case, then let's now try to find the sum to infinity. What does it mean? We are saying, as we continue adding terms, what's going to happen eventually to our Tn as the terms become bigger and bigger and bigger? You notice, if I were to continue with this series, my next term here will be 1 over 32. My next term 1 over 64. And we continue. So our terms, the denominator continues to grow throughout. At some stage, we are going to come to probably some 1 over a million or a billion or whatsoever. And if we try to check what that is, we actually approach 0. We are dividing 1 by a very large number. Okay? So we are saying there will come a point when our terms now essentially are sitting at 0. So if at some point we are now just sitting with 0 plus 0 plus 0 plus 0 plus 0, it means that our series is converged. It doesn't matter what we do now, our sum remains the same. That's what we mean by a sum to infinity. Okay? Now, let's now try to calculate that sum to infinity for this particular series. From the sum of n terms for a geometric progression, we managed to see that if we want the sum to infinity, it's a very simple thing. It's a over 1 minus r. The first term divided by 1 minus the common ratio. It's easy here. What is a? It's half. What is r? It's half again. So we are saying the sum to infinity will be equal to a, which is half, divided by 1 minus half. If you notice, this is the same as half divided by half. Half divided by half obviously is going to give you 1. So we can safely say our sum to infinity for this series is equal to 1. Then I'll explain what that means. Okay? S infinity is equal to 1. What does that mean? It means that if we were to take all these terms that we're adding, all of them, continue and add as many as you want. If you're going to add everything, we will come to 1. Why? Because eventually at some point, the terms are going to come down to 0. But for this particular case, our sum to infinity is equal to 1. Let's take a look at a practical example of how to use this which we've just learned. Let's take a look at the following. At the following 2 recurring decimals. And then we try to use what we've learned, think about what that recurring decimal really means, and see how we can actually apply this sum to infinity to such. Let's take a look at 0.6666. 66666 recurring and continuing like that. I'm sure there's so many cases where you've tried to find a fraction, calculate a fraction, input a fraction into your calculators, which I know you love very much, and you come up with such kind of a thing, an ever-ending decimal, a recurring decimal. If we were to ask ourselves, what does that mean? Let's check. Here we see that we are sitting with the following. 0.6. 0.6 is actually the same as 6 over 10. You can do that in check. Right? Then, to this, we're adding a 0.06. See? 0.6. So this is 0.6. Then we add a 0.06. We get 0.66. Correct? Then we add a 0.006. We get 0.666. And we continue, we add a 0.0006. And then we bring that, and we continue building that up. If you try to think, what does that mean? 0.6 we have said is actually 6 over 10. And we are saying to that we add 0.06. 0.06 is actually 6 over 100. And we are saying to add the other term, we add 0.006, which is 6 over 1,000. Plus, we can continue. Obviously, the next term to come here is 6 over 10,000. Plus, until we add whatever that we add at the end. Now I'm going to ask you a simple question here. If you notice, we've already taken, we have actually gone on to transform this recurring decimal into a very simple series. Yes. Let's try now to ask ourselves, what kind of a series is that? An idea? I'll tell you, it is geometric. What are we doing? Obviously, if we were to do what we do with every other series, we will notice that AE is equal to 6 over 10. That's our starting term. If we want to try to find a common ratio, we know that our common ratio is Tn over Tn minus 1, a term divided by the term before it. So if we were to look at these as terms, obviously this would be our T1, this would be our T2, this would be our T3, this would be our T4, this would be our T5, and we can continue to any Tn that we feel like. Right? So if we want to find that common ratio, we can take any pair, divide a number, a term, by its predecessor and see what we get. Let's take T2 divided by T1. That's obviously 6 over 100 divided by 6 over 10, which is the same as times 10 over 6. One over 10. Let's take T4. Let's take T4 and T3. T4 divided by T3. That's 6 over 10,000 divided by 6 over 1,000, which is the same as multiplied by 1,000 over 6. 661, 661, and we can see the three zeros, and again we are left with 1 over 10. We can do that with T3 and T2, and you still see that we get 1 over 10. So we convince ourselves here that, look, we are sitting with a simple geometric progression, and 6 over 10 plus 6 over 100 plus 6 over 1,000 plus 6 over 10,000 plus. And we've said that AE is equal to 6 over 10. Our common ratio, we've just found it, is 1 over 10. If we try to think now, that common ratio, it's a simple fraction. You can see that. It's a fraction. The denominator is actually bigger than the numerator. So it's a number which is lying in this region between 0 and 1 and minus 1 and 0. It's a simple fraction. It's not a whole number. And if you try to think about it, if you were to make this grow, to make our denominator grow as we add our terms, we would be actually dividing 1 by a very big term. So eventually we will come to 0. Okay, now let's check. If we want now to find what this fraction is in simple terms, obviously nobody wants to write a fraction, a number like that, which is actually never ending. Let's see if we can actually write that in a simpler form. What does that mean? We are saying, like what we've said here, all these terms essentially the same as this plus that term plus the next 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 term to give you that simple decimal, or that recurring decimal. So if we want to find what all this gives us, we'll say, okay, fine. What would happen then if we were to add all the terms? If we add all the terms, then obviously we're talking of sum to infinity. So the question would be, what is the sum to infinity of this series, of that recurring decimal? And we know, we have said that our sum to infinity is obviously our first term. We have derived that on our own, so we should be happy about that. over 1 minus the common ratio. But what is a in this case? It's actually 6 over 10. So this is the same as 6 over 10 over 1 minus 1 over 10. If you notice, 1 minus 1 over 10 is exactly the same as 9 over 10. So we are saying this is the same as 6 over 10 divided by 9 over 10. This is equal to 6 over 10 multiplied by 10 over 9. 10, 10, that goes away. 3 into 6, 2. 3 into 9, 3. So we are saying that our sum to infinity is equal to 2 over 3. Correct? Now let's check what that means. S infinity is equal to 2 over 3. Let me explain what that actually means. It means that this recurring decimal that we're seeing here is essentially 2 over 3. For those who love calculators, go to your calculator and punch 2 over 3. You will get 0.666666666, never ending. And we have seen how we can actually manipulate a simple recurring decimal like this one into a progression, whose sum to infinity we can easily find. Happy? Yes. Good. Now, we will do a lot of those in our tutorial. So our tutorial DVD will be able to deal with all that, where we are not talking much in terms of trying to give out a lesson or lecture. We are simply working out problems using the principles that we've actually learned here. So these discs are going to come as two, the lesson and the tutorial. Okay, good. Now, let's go on to introduce something very much related to series. And take note of this. The sigma notation. Or the summation sign. Right? What does that mean? I'll explain to you. We have noticed that up to now, we've always been writing our series as T1 plus T2 plus T3 plus T4 plus Tn. The question is, can't we find a very good way of shortening, all this? Probably just write it, as one little thing, and whenever we want to expand that, we get exactly this. Yes, we can. We use what we call our sigma, we use what we call the sigma notation, or the summation, the summation sign. We usually write it like that. Oh, let me write a bit better. That sign, whenever we are going to come across it, immediately we should think of summation. We are adding things. What does it mean? It means we will, okay, let me try, because I know for some of you it's probably the first time that you're seeing it, but that doesn't matter. So normally we'll come and say, okay, fine, let's do the following. Give you a number n, or whatsoever term n, or like we actually have now. And then we say, okay, fine, let's say to some n. What does that mean? Listen carefully. This is what we mean this is what we call our index of summation. It's two, starting point, end point. That's the term that we're actually dealing with. When you write something like that, what we are saying is that, look, you have got n. We want you to start from n equal to 1. Natural counting. We start from 1, we go to 2, we go to 3, we go to 4, 5, 6, 7, 8, 9. Adding 1, of course, at a time, like what we've seen with natural numbers already. So when we give you that, all we are saying is, okay, fine, do the following. Start at n equal to 1. If n equal to 1, then of course, I'm starting at 1, n equal to 1, so I'll write 1. Then what we want you to actually do next, move from 1 to 2. So now, and n. So now if I'm going to move, my n now is not 1, because I'm now at 2, it's now 2. So plus 2. Move again from 2 to 3. So my n now is 3 plus 3. And continue until you get to n. Suppose our n is 5. So we say, okay, obviously, after moving from n equal to 3, I'll go to n equal to 4. If n is equal to 4, then what I'm adding is 4. Then eventually I'll end at the point 5 plus 5. And if you check, our sum here should be equal to 3, 6, 10, 15. If you try to think about it, what is this really? This is a series. An arithmetic series with the first term equal to 1, with the common difference equal to 1. The only thing that we're doing here is to add 1 to a term in order for us to get the next term. So we've just found a way of writing the first series that we actually work with. 1 plus 2 plus 3 plus 4 plus 5, or plus 6 plus 7. In general, we can write it as n equal to 1 to n if we want. But if you were to ask yourself, how do we know that? Effectively what we've done is, we have given you something which gives you a term every time. And then you move from term 1, term 2, term 3, term 4, term 5. So this is the expression for your term. Can we prove that? Yes, we can. If we remember what we said about arithmetic series and sequences, we say that the nth term is equal to a plus n minus 1 d. If we look at what we have there, what is it that we have? We have the following. A we know is 1. Correct? Good. If A is 1, what is D? D is 1. Correct? So, if we want to find Tn, our nth term, unique to this series or to these terms, how do we do that? Tn therefore is equal to A, but we know that A is equal to 1, plus n minus 1. We don't know n, but we know d. D is equal to 1. So this will be the same as 1 plus n minus 1 times n minus 1 times 1 is actually n minus 1. So we end up with Tn is equal to n, because 1 minus 1 is actually equal to 0. Now if Tn is equal to n, you can see where that n is coming from. We are saying if you take the general or the unique nth term, Tn, to a series, you can easily write it in this form, using the sigma notation. Obviously we know that when you're starting when you're working with sequences and series, we start counting from 1. We don't talk of term 0, we don't talk of term minus 1. That's why we're starting at n equal to 1. Okay, let's take a look at an example and see if we can actually convert a series that we know or represent it using the sigma notation. Let's take a look at the following. 2 plus 5 plus 8 plus 11 plus 14 plus. Right? Obviously, is at the stage that we are now, that we are at now, we have to ask ourselves simple questions. What kind of a series is that? Is it arithmetic or geometric? In both cases, we know that, okay, fine. We always are going to have a starting term. Our starting term here is equal to 2, so A equal to 2. Now the next question will be, do we have a common difference or a common ratio? So we check. Let's try to check first. Do we have a common difference? A common difference, if we do have, we know it will be Tn minus 1. So a term minus this predecessor, a term minus this predecessor, they should always give us that common difference. So if we check, T2 minus T1, 3. T3 minus T3 minus T2, 3 again. T5 minus T4, 3 again. Then we stop. Already we see that we are sitting here with an arithmetic progression, an arithmetic series. And we've got a common difference, D equal to 3. Good. Now, if we want to represent that simply using the sigma notation, how do we do that? We simply have to find Tn. That's what we're going to plug into that nice looking thing. Tn, for a simple arithmetic progression, we know that Tn is equal to the first term plus n minus 1 d. You derive that on your own. You actually managed to get that on your own. So if you want the nth term unique to our series, then Tn is equal to a, but we know what a is. It's 2. Plus n minus 1, we don't know n, but we also know what d is. It's 3. Right? So if you're going to expand that bracket, we get 2 plus 3n. 3 times n, 3n. 3 times minus 1, minus 3. So you notice we end up with 3n minus 1. Or minus 1 plus 3n. It doesn't make a difference. So our nth term, therefore, unique to that series is 3n minus 1. If that is the case, then how can we write this series using our sigma notation? Our sigma notation, once we have our Tn, will always be the term unique to the series, and obviously we start from term 1, and we can get to any other term, n. So, what is Tn? We have seen that here, Tn is equal to 3n minus 1. So this whole series can easily be represented or be written as 3n minus 1 summation from n equal to 1 to n. Let's see if that is true. Let's do exactly what we did earlier. If you want to write the terms of this summation as given, we'll say, okay, let's start. This is equal to, when we start, n equal to 1. Right? So, 3n minus 1 will be 3 times n, but we can see n equal to 1 as we're starting, minus 1. Correct? Yes. 3 times 1 minus 1 is 2. So we can see that our first term will be 2. Plus, we now move from n equal to 1 to 2. So now n equal to 2. So what do we have? 3 times n, but n is equal to 2 now, minus 1. 2 times 3, 6, minus 1, 5. So plus 5. Plus, we move to the third term, n equal to 3 now. So this will be 3 times 3, 9, minus 1, 8. Plus, we move to the next term, n is now 4. So 4 times 3, 12, minus 1, 11. We move to the next term, n equal to 5. 3 times 5, 15, minus 1, 14. And you can continue. So do you agree that this represents that exactly? These two things are actually identical. So this is a very nice way, unique way of writing a series. Now I'll ask you a question. Okay, fine. Before we actually ask a question, let's take a look at another series, but a geometric one. This one, this time. And we'll be very fast with this one because we now understand all the concepts that we actually need to know about series for now. Suppose we have the following. 1 minus 1 over 3 plus 1 over 9 minus 1 over 27 plus 1 over 81 minus 1 over 243. I know this might look very confusing to you for now, but actually it's not at all. What kind of a series is that? Tell you up front, it's geometric. In any case, if we were to think about it, let's assume it's actually a series until we prove it not to be. Okay? Like with any other series, we have got a starting term. Our starting term A is equal to 1. Happy? Good. The next thing I'm telling you is geometric. Let's see. So let's not worry about trying to find a common difference. Let's see what if it's geometric, then we should actually expect to have a common ratio. Happy? Right. If that is the case, we know that to find our common ratio R, it's always Tn divided by Tn minus 1. A term divided by a term before it. So let's take a look at T2 over T1. Say T2 is minus 1 over 3. You can see that there. So okay, fine. Let's explain this part. T1 is plus 1. This one, which is the same as plus 1. T2 is minus 1 over 3. T3 is plus 1 over 9. T4 is minus 1 over 27. That's what this sequence is actually doing. So if you want to find T2 over T1, this is the same as T2 minus 1 over 3 divided by 1. Minus 1 over 3 divided by 1 is equal to minus 1 over 3. Happy? Good. Let's see if for sure our common ratio is consistent. So if that ratio is actually inconsistent, then of course we'll say, yeah, we're actually sitting with the common ratio. Let's look at T3 divided by T2. This term divided by that. T3 is 1 over 9 divided by T2, but T2 is minus 1 over 3. So divided by minus 1 over 3. This is the same as 1 over 9 multiplied by minus 3 over 1. 3, 1, 3, 3. So we actually end up with minus 1 over 3 again. Let's look at any other term. Let's look at T6 divided by T5. Minus 2 over 43. Sorry, minus 1 over 243 divided by 1 over 81. This is the same as minus 1 over 243 multiplied by 81 over 1. 81 into 81, 181 into 243, 3. And again we've got minus 1 over 3. So we should then agree that we've got a common ratio there, but the only thing that's making this thing look a bit difficult or funny is because our common ratio in this particular case is negative. So R is equal to minus 1 over 3. Let's ask ourselves, what does that mean? R is a simple fraction. Yes, it is negative, but it's a very simple fraction. The denominator here is bigger than the numerator. So it's a number which is lying between minus 1 and 1. Or minus 1 and 0, as we say. Therefore, we expect our series to converge again. Happy? If we are happy with that, then if we want to express this using our sigma notation, what do? Like with any other series, we need to find the nth term unique to the series. But we know, for a geometric progression, or for a geometric sequence, even, the nth term Tn is equal to the first term times the common ratio to the power n minus 1. Happy? Good. If that is the case, how can we make this unique to this series? Of course, it's easy. We can see that A is equal to 1. We can see that R is equal to minus 1 over 3. So, we are going to have the following. Tn is equal to A, but we know that A is equal to 1. To the power R, but we know that R is minus 1 over 3. Let me put that in bracket. Then to the power n minus 1. So we can rewrite this uniquely as Tn is equal to minus 1 over 3 in brackets to the power n minus 1. Let's think about something here. Very interesting, very nice. If my power, if it is even, right? If it is even or 0, this is what we see. Let's say my power is 0. n minus 1 is 0. So everything is 0. Minus 1 over 3 to the power 0 will be 1. Which is that. And I want you to take note. 1 is written like that is positive. Let me say this power is even again. By even I mean 2, 4, 6, 8, 10. An even number. Suppose this power is 2 now. which means n is equal to 3. 3 minus 1 is actually going to give you 2. Then you are going to have minus 1 over 3 to the power 2. This is the same as minus 1 over 3 times minus 1 over 3. Minus times minus plus. 1 over 3 by 1 over 3, 1 over 9. So plus 1 over 9. And we can see our plus 1 over 9. So I want you to see something. Whenever our power is going to be even, our term is going to be positive. Can you see that? But when our power is going to be odd, by odd I mean 1, but of course remember, 1, 3, 5, 7. If I've got a power 1 here, so n minus 1 equal to 1. When is that possible? Sorry. If I've got a power 1, so for example, n minus 1 equal to 1, that means n equal to 2. So that 2 minus 1 actually gives me 1. Then I'll be left with minus 1 over 3 to the power 1, which is minus 1 over 3. And we can see that here. Good. If I'm going to have n equal, my power is 3, then it means that n equal to 4. N equal to 4 minus 1 gives me 3. So I'm going to have minus 1 over 3 to the power 3. What does that mean? It means minus 1 over 3 times minus 1 over 3 times minus 1 over 3. Why are we getting a negative? Simply because if we multiply a negative or negative numbers, we multiply them in such a manner that it's even, for example, twice. Or rather multiply, twice. Minus 1 over 3 times minus 1 over 3, that's actually going to give us a positive. Minus and minus. Positive. So that's actually going to give us a positive 1 over 9. But now I'm forced to multiply a positive number with a negative number. So I get a negative. If I were to have it as 5, as an example, my power is now 5, which means n equal to 6 here. This would actually give me minus 1 over 3 to the power 5. Minus 1 over 3 times 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 minus 1 over 3. Check what's actually going to happen. Minus times minus, that will give me a plus. Correct? Minus times minus, that will give me a plus. But now I'm left with a minus. So I'm now multiplying a plus with a negative. That's why we end up with a negative term. Okay? Minus 243. Minus 1 over 243. But anyway, we just want, so we can write this. That you know what? We can rewrite everything if we feel like. We can actually go on to write this as our nth term, Tn, is equal to, right, plus or minus 1 over 3 if you want, to the power n minus 1. And we state one special condition. It will be negative or positive when n is odd. I'll explain why. And also write that it will be negative when n is even. You know why? Initially we're saying the power has to be even for us to have a positive term. The power has to be odd for us to have a negative term. So why are we now saying that when n is odd? Because when n is odd, n minus 1 becomes even. Let's take an odd n, like 5. Then 5 minus 1, my power now will be 4. And once we have that, then it actually becomes positive. Let's take n is actually even, say 4. Then my power becomes odd. 4 minus 1, 3. And now I'm multiplying 3 negative terms together. So we can easily rewrite that, but it doesn't matter, we can still leave it here. Right? If that is the case, we have said that our unique Tn for this particular sequence, Tn is equal to minus 1 over 3 to the power n minus 1. So it means that we can use our sigma notation to summarize this series. How? This way. Obviously we start a series with our first term to any other term that we want n, and we'll be adding the term. So Tn from term 1, term 2, T1 plus T2 plus T3. But we know what Tn is. It's minus 1 over 3 to the power n minus 1. So we can represent this whole series simply like that. Can we check if that is true? Yes, let's do that. So we try to expand that summation and see what we get. If n equal to 1, then our first term obviously will be minus 1 over 3 to the power n, but we've said n is equal to 1. 1 minus 1, 0. Correct? Yes. Plus n equal to 2. But what is n? Sorry. Now n equal to 2 is we move to the next term. So plus minus 1 over 3 to the power n minus 1. But n equal to 2 now. So 2 minus 1 we get 1. Plus n equal to 3 now. So minus 1 over 3 to the power n. But n minus 1 will be 2. So that will be 3 minus 1, which will be 2. And we can continue. Can you see that? In fact, from now on you can see. We can actually, when we come here, it's now minus 1 over 3 to the power 3 plus minus 1 over 3 to the power 4. And you can continue plus, 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 plus. Let's see if this is exactly the same as that. Right? Any number to the power 0 is 1. So this will be 1. Plus minus 3 to the power 1. That's minus 1 over, sorry, minus 1 over 3 to the power 1, that's minus 1 over 3. Plus minus 1 over 3 squared. What is minus 1 over 3 squared? That's minus 1 over 3 times minus 1 over 3, which is equal to 1 over 9. Plus 1 over 9. So plus 1 over 9. Correct? Then we come here plus minus 1 over 3 cubed. That's exactly the same as minus 1 over 3 times minus 1 over 3 times minus 1 over 3. Minus minus plus minus minus. 3, 3, 9, 3, 27. So 1 over 27. So we get minus 1 over 27 here. And we can continue. And you can see already, this is exactly the same. So do you agree then that we can actually write series in short by simply finding their unique nth term and putting it in this form, beginning with n equal to 1 to any other n that we want. Equally, if somebody had come to us and said, fine, now I understand that, okay, you can use that sigma notation. Can you please find the following for me? What does it mean? Let's just do this and then conclude our lesson. And that'll be it. If somebody now had come to you and said, from n equal to 1, as expected, minus 1 over 3 to the power n minus 1, but I want you to go all the way to infinity. What does that mean? It's very simple. We have already seen that this is exactly the same as that series. In one case, of course, we limited ourselves to some nth term. Now someone is saying, go all the way, add everything, up to the term approaching plus infinity. So everything, every member of this series, add it together. Let's see what will have. But then if you remember, we said that once we do that, this is exactly the same as the sum to infinity. So if you want to find, so this is exactly the sum, is exactly the same as the sum to infinity, but you know that s to infinity is a over 1 minus r. So we can then go on to say, but no, that's not very difficult. If you want to find the sum to infinity, which obviously has just been written slightly differently, but exactly the same thing, it's a over 1 minus r. Our a we know is 1. 1 minus r is 1 minus, but what is r is minus 1 over 3. You remember? So, this is the same as 1 divided by 1 plus 1 over 3. What is 1 plus 1 over 3? You can check with me. It's obviously 1 plus 1 over 3. Common denominator 3. Remember that's 1 is the same as 1 over 1. 1 into 3, 3 times 1. 3 into 3. 1 times 1, 1. So this is the same as 4 over 3. So we are saying this is actually the same as 1 over 4 over 3. So 1 divided by 4 over 3, which is the same as, which we can write simply as 1 divided by 4 over 3, which is the same as 1 multiplied by 3 over 4. Correct? 3/4. So we can come back and write that. The sum to infinity of this particular series is 3/4. What is the meaning of that? It means that if we at the time, or let's say we are actually programming a computer to do the following addition and do all the terms. If we were to add all of them, what you would get is a simple 3/4. Happy? Good. We conclude this lesson. In our tutorials, we will also see that we will work with a number of things which might look slightly different. For example, your so-called financial mathematics, those compound interests. We'll look at sequences or series where we are having squared terms, right? Like 1 squared plus 2 squared plus 3 squared, which we haven't looked at yet, but it's pretty much deliberate because we'll notice with our knowledge that we have already, we'll be able to work all those things out. If you're given that you've gone to a bank and they tell you, okay, we're going to give you a mortgage, every month or maybe say at the end of the year we are going to charge you so much interest. You pay away or you pay or you repay so much. At the end of the year again we come and we charge you that same interest and then you end up compounding that interest. Can we use the knowledge that we have here to calculate our repayments, to calculate our bond length, etc, etc? Check our tutorial video, we'll be doing all that. So we'll look at all your past exam papers from 2008 to 2012 in that. Thank you.